Hello, everyone. It's my great pleasure to introduce our first speaker, Professor Iztok Peterin from the University of Maribor in Slovenia, in particular from the Institute of Mathematics and Physics at the Faculty of Electrical Engineering and Computer Science. He is an author of many papers concerning graph theory, namely, in particular in metric graph theory, graph products, different models of graph colorings, dominance, so many topics and many papers, many achievements. So even more, it's a pleasure to me to introduce him. And please, Iztok, it's your time now.
Hannah, thank you very much. I need to give you an explanation. I'm here as a Leonard. Leonard is my son, and he's using usually Zoom. We are using some other tool at the university, so this time I will be Leonard. Okay, I'm still Iztok. Yes, today I will talk about two versions of coloring algorithms, and let me share the screen with you. Okay, where it is, share. I hope you see it, and just full screen. Okay, so the idea is now already old for some decades, even half a century for the other, and coloring is actually a hard problem if you want to get it done optimally, so with minimum number of colors. And because of that, one wish to have some algorithms which produce colorings, but maybe not optimal colorings, and they are fast. And the question is, how much can we miss by these polynomial algorithms which are not optimal? And I will talk about this, and because I will start really slowly, even by the definition of a graph. So as you probably know, graph is defined by two sets. One set is a vertex set, and the other set is edge set. Vertex set is denoted by, sorry, just a moment. Okay. This is a vertex set, and this is an edge set. And in vertex set, we have some elements, doesn't matter what, it can be anything, but the edge set is then kind of limited and contains unordered pairs from vertices. So there not need to be all unordered pairs, but some unordered pairs. So we will use the notation for unordered pair. We will just write UV, and this is then an element of an edge set. What does this mean? We can visualize this graph. First, we draw vertices by like points in some plane, let's say, on a board or on a paper, and edges are then presented as some lines between the vertices U and V. This line, it can be straight, but it is not necessary. So here is one example. So you see these circles, these are vertices, and some vertices are adjacent by an edge, and some vertices are not. So for instance, this red vertex now is not adjacent to this blue vertex because there is no edge, there is no line between them. Why is this model very successful? Because one can really, with this graph, one can model so many different things, so many real life situations. Just let me just mention some of them. Any network system can be modeled by that, like electricity, road, railways, water supply system. Very important is internet, of course. Internet can be modeled by a graph. Of course, this is a huge graph, but we are living in modern times, and things must be are mostly huge. Social media, very popular recently. Facebook, Twitter, Instagram, and so on. Vertices are users of these social medias, and if they two of them are, let's say, friends, then we put an edge between them, and no edge if they are not friends. Molecules in chemistry can be modeled by graphs, and it's a huge part of a graph theory. Intersects with chemistry, actually. Social contacts for preventing the spread of viruses, for instance. This is very, let's say, popular. We don't want to be popular, but it is. So we are in this COVID pandemic, and again, everything can be modeled by graph, and much more. Okay, this is just a short introduction, but now let me give us some notation which will be important later. So we will need a click number, or the click number, which is denoted by omega of g, of a graph G, and this is a maximum cardinality of a set of vertices, subset of vertices, such that between any two vertices of this sets S, we have an edge. Shortly, there will be, okay, here it is. So if you observe on this graph all the vertices which are colored red, you can observe that between any pair, we have an edge, we have a line, and this means that this is a clique, and we are interested in clique number, and this is the maximum number of vertices with this property, and on this graph you will not find any bigger. So maybe just to mention, if you take this 3 red and these 2 blue, then we have again a clique, but it is of cardinality 5, so it's smaller than before. Okay, what are blue vertices on this figure? Blue vertices on this figure are representing the open neighborhood of vertex V. This is this set, and V is the black vertex on this figure. So open neighborhood of a vertex are all vertices that are adjacent with the starting vertex, which means that they form an edge with this vertex V. So this is open neighborhood, and we also know about close neighborhood, and close neighborhood is open neighborhood together with original vertex V. So close neighborhood on this figure of this black vertex is all the blue vertices plus this black vertex. Okay, and now already to the main topic of this talk, two colorings of graphs. A coloring actually is a map which put every vertex, to every vertex is given a color, which is usually just said, these numbers from 1 to k are just usually said that these are colors. And such a map is a proper vertex coloring. I will later not use the word proper because every coloring about which I will talk here is a proper one. So just a vertex K coloring if two adjacent vertices receive different color. So if we have an edge in a graph, then its n vertices must receive different color. And every such coloring splits the vertex set into some subsets which are called color classes. And this is one color class. And this is a color class of color I. So in color class VI are all vertices which have color I, which are mapped into color I. So sets from V1 to Vk form a partition of vertex set, which is, I believe, clear. And now, what is the chromatic number? The chromatic number first is denoted by high of G. And this is the minimum integer K for which there exists a vertex K coloring. So the smallest K for which we have a coloring. Some really well-known fact is that high of G is greater or equal than omega of G. Why is that? Omega of G is a clique number, so every two vertices are adjacent. This means that every two vertices from this clique needs to receive different color. And this is already the reason why this inequality holds. Okay, here is one coloring, and maybe you can observe that all these vertices which are in this clique from before have different colors. So you see yellow, black, orange, red, blue, and violet. But actually, these are not the only colors here. We also have a green color in two vertices. So here and here. But orange, yellow, and black are repeated outside of this clique. So this is 7 coloring. Okay, I have some problems with writing. Coloring with 7 colors. Okay, that's better. Okay, here is another coloring of the same graph. Again, this clique contains only different colors. In this example, yellow, black, green, red, blue, and violet. And all the vertices outside, red is already here. Okay, here is also red. So no, yellow is already in this clique. Black is also in this clique. Green is also in this clique. So all the colors which appear outside of this greatest clique are also in the clique. So we have 6 coloring of this graph, and therefore high of G is 6 coloring, because we said that omega of G is the lower bound for this parameter, this invariant anyway. Okay, some really well-known facts about coloring. This is an NP hard problem. If you don't know what this means, doesn't really matter for us right now, but this means that there is no polynomial time algorithm yet. Many people believe that it does not exist, such an algorithm, and therefore this means that we need a lot of time to derive this invariant. Okay, another thing, but we can say for some simple examples, we can say some exact results, and we can say when the graph has chromatic number 2, this happens if and only if G has no cycle of odd length. And this is actually if and only if G is bipartite. Again, if you don't know what is bipartite, it's not really important for this talk. Okay, but there exist some graphs where phi of G can be arbitrary, but omega of G is 2. This means that omega of G is 2. This means that there are no triangles in graph. And this is a kind of surprising result for if one meets this problem for the first time. But there is a relatively easy construction to obtain such examples. And this is done by Michelski graph construction from a triangle-free graph. And at each step of this construction, one receives a chromatic number for one bigger than the previous graph. So the graph remains without triangles and the chromatic number goes up. Okay, also let me mention the famous four-color theorem. This means that for every planar graph, we can color it with at most 4 colors, maybe with 2, 3, but 4 is definitely enough. And the proof for that was done actually by a computer in 80s of the previous century. So, as mentioned in the introduction, because this problem is NP hard, we are interested in simple algorithms that produce colorings of G. But these colorings are sometimes they are optimal, sometimes they produce the best coloring with the minimum number of colors, but often not. So we are interested in what is the difference between what these algorithms are giving us and the chromatic number. By the way, such algorithms are called heuristics. So they give a kind of solution, but this solution is not optimal. And we will observe in what follows 2 such approaches. One, we will call it a reducing algorithm. Actually, this I'm not sure that this name is used in the literature. Actually, I did not found any name in the literature, so this is just my invention. If there is something, I'm really sorry. And the second one is greedy algorithm. This one is much more known and is sometimes also called first fit algorithm. Okay, so we will start with this reducing algorithm, and let us start with a definition of b-vertex. So suppose that we have some coloring C of graph G, and this is represented by this partition from V1 to Vk. And we call a vertex from Vi a b-vertex of color I if there exists a neighbor of V of color J for every J which is different than I. This is important, for every J different than I. This actually means that the close neighborhood of V contains all the colors. So V is has color I, and all the rest, all the all the remaining colors, one can find a neighbor of V of this color. So in the close neighborhood of V, we have all the colors. So what does this mean? If we would like to recolor a vertex, this means that, so what does this mean, recolor a vertex? To change it to some other color. This means that B vertex cannot be recolored by any existing color because we already have all the colors in its neighborhood. So what is the idea? Maybe I will tell you the idea of this reducing algorithm. If we have a color class, then we would like to recolor all the members of this color class Vi. And to do that, we are not allowed to have B vertices in this color class. And this is written actually here. So if we have a B vertex of color I, then we cannot recolor every vertex of color I, and color I cannot be reduced. So we are interested in the color classes without B vertices, and such color classes can be at some stage recolored. So every member of this color class can be recolored by some other color. Not all the vertices with the same color, but maybe with different colors. Okay, so again, we have a coloring, k-coloring of graph represented with this partition. If every color class has a B vertex, then we immediately stop because we cannot recolor any color class. So we are interested only if there exists a color class for let's say that this is VK by possible exchange of colors, such that VK is without a B vertex. So every vertex in this color class can be recolored by some other color, and we will reduce this K coloring to K-1 coloring. And this is formally done like that. So we introduced a new coloring, C prime, and this C prime is the same as C as soon as the color of V is different than K. But if the color of V is equals to K, then we choose a color IV, and IV is some color from set of colors from 1 to K-1, and such a color exists because V is not a B color. So we take a color which is not present in the open neighborhood of vertex V. And this C prime is actually K-1 coloring. So we receive less colors, and that's fine because we are hoping to get a minimum number of colors. And if this procedure is repeated, then sooner or later we end with such a coloring that every color class has a B vertex. But until then, we can repeat this procedure. And this is called a reducing algorithm. Now the question here is, with what do we start? Which kind of coloring we start? We can start with coloring that has where every vertex has a different color. Of course, this is not maybe the best and optimal way, but still, if we start like that, nothing can go wrong. Okay, and further, we say that this new color C prime is in relation Q with old color C. So this color with less colors is in relation with coloring C, from which coloring C prime was obtained. Okay, an example. You see here is a coloring, and if you analyze this, you will see that this green vertex is not a B vertex because it is not adjacent to this orange one, and also this green vertex is not a B vertex because it is not adjacent with this yellow vertex, so no yellow vertex in its close neighborhood. So this means that this green color can be reduced, and as mentioned, this orange was missing in the close neighborhood of this vertex, so it can be orange, and a yellow was missing in the neighborhood of this vertex, so it can be yellow. So we did reduce this coloring for 1, and no further reductions are possible here. But anyway, we obtain a coloring, 6 coloring, and we know that this is optimal. Okay, what is the time complexity of this algorithm? N of G is the number of vertices, M of G is the number of edges. At most steps of this algorithm are N of G minus 2. So the least number of colors is 2. So this is O of N of G. I mean, we could do it better. Instead of 2 here, we could replace it by high of G. But okay, we just want to show that this is a polynomial algorithm. Okay, what is how do we check if every color class has a B vertex? Actually, if we want to do it for the whole graph, we need to scan open neighborhoods of all vertices in each color class, which means that for every vertex, we check all its neighbors. And this is actually the degree of a vertex. And by handshaking lemma, we know that this is 2 times number of edges, and this is actually, of course, O of M of G. But again, this is way too generous. We could reduce this calculation, because when we find B vertex in one color, then this vertex by this reducing algorithm will not will remain a B color after each step. So we don't need to check all the vertices all the time, but only those which do not have a B vertex. So this can be reduced, this O of M of G. And moreover, by recoloring vertices of a color class, we always recolor less than N of G vertices, and this is O of G again. So altogether, we have N squared times M, and as mentioned, this is too generous. We could reduce this further, but for us it is important only that it is polynomial. Okay, now original definition of a b-chromatic number, which will be done now by Irving and Manlove from 1999, is the following. We defined the relation Q. Let Q bar be the transitive closure. And if the transitive closure is then strict partial ordering of all proper colorings of graphs, of graph G, which means we have finite many different colorings of G, because we are talking about finite graphs. And if we have finite, this means that Q bar has some minimal elements. Okay, and the maximum number of colors used in a minimal element of this ordering Q bar, so of this transitive closure of Q, is then called b-chromatic number. The symbol for it is high B of G. So this means maximum number. This means the worst possible case when we obtain such a B coloring. So this is the worst case that can happen by this reducing algorithm. Okay, and if we take minimum number of colors in a minimal element, then we obtain high of G. So this is a kind of, then this high B of G, this b-chromatic number, is kind of dual because of that, of high of G. Okay, we could also call it the upper chromatic number because of that. Similar situation we have by domination number, and there is something called upper domination number. Okay, the theorem is as follows, and it is very normal one, and one could expect it. So the b-chromatic number of graph G, which is denoted by high B of G, is the largest integer k because of this maximum from before, such that G admits a proper k coloring in which every color class contains at least one B vertex. Because if we have B vertex in every color class, we cannot continue with reducing algorithm. And largest integer k, because we are searching for maximum. So this is not unexpected, and it's very useful. So here, this coloring, we have met this example for often now. We can see that we have a 7 coloring, and now just observe that every color class has a B vertex. So this black vertex has neighbors green, yellow, blue, violet, red, and orange. This is a B vertex for yellow color. So in the neighborhood are green, black, orange, red, blue, and violet, and so on. This is a B vertex for violet. This is B vertex for blue. This is a B vertex for red. But this one, this orange one, in this clique is not a B vertex because it has no green neighbor. But this vertex is a B color of B vertex of orange color, and this is a B vertex of green color. So we have B coloring with 7 colors, which means that 7 is the lower bound for high B of this graph G. And we recall that the chromatic number was 6. So we can have, of course, different values of these two parameters. What are typical bounds? So for the lower bound, it's very easy. The chromatic number is, of course, the lower bound, but for upper bound, we have a very natural upper bound, and this is because every B vertex must have big enough degree, at least so much. Otherwise, it cannot have all the colors in its neighborhood. So we can expect this upper bound with connection with degrees of vertices. I did not formally said, but degree is the number of vertices in its open neighborhood. So here is the definition of M degree, and it is like that. M of G is the biggest position, so maximum position, where the degree of a vertex Vi is greater or equal than I minus 1. And let me mention that the vertices are positioned like that they are ordered with respect to their degree. So we start with the maximum degree and proceed by falling. So the degree of V1 is greater or equal than degree of V2 and so on. Okay, this is for regular graphs. This is very simple because position, you see in regular graph, every vertex has degree R. And this means that R plus 1 position has degree, of course, R. So this is R. And it needs to be bigger than R plus 1 minus 1, which is R. And that's whole. So for regular graph, M degree is always R. For our regular graph, M degree is always R plus 1. And now we have these trivial bounds. The lower bound is chromatic number and the upper bound is M degree. And moreover, this M degree can be computed in polynomial time easily. Okay, let's go to the same example. So we have positions here, 1, 2, 3, 4, 5, up to 11, and the degrees. 7, 7, 7, which vertices are of degree 7? I think that this red, this blue, and this violet. And then we have 4 vertices of degree 6, and this is this black, this yellow, this green, and this orange. And then a vertex of degree 5, this is this orange, and then 2 vertices of degree 3, these are these 2, and we end with vertex of degree 2. And now see the biggest position, so that this number is greater or equal than this number. And this is 7 in this graph, and we have a coloring, B coloring with 7 colors, and this means that high B of G is 7, which equals M of G in this particular example. Okay, another, let me check what is the time. So maybe I will be a little bit faster now, but now there are some examples. First of all, for complete graph, we have that chromatic number and b-chromatic number is the same, which is less or equal n plus 1, which is M of G. Of course, the equality holds only if n is 1, actually. Okay, so you see, we did change this. Okay, this black should not be black, but should be white. And we did change this white to the violet because there are no, because this violet and this white are not B vertices. Now we can continue similarly, and you see this blue and this red are not B vertices because they have no violet in their neighborhood, so we can recolor this red into the blue. Okay, now we have that, and next step, okay, this black is not a B vertex because it has no orange, for instance, in his neighborhood. So this blue, black can be recolored to green, and now again, this orange is not a B vertex, or this color class has no B vertex because it has no yellow, and it can be recolored by green, for instance. Now, next step, blue and violet. Okay, violet are not B vertices because they have no blue color, and they can be recolored into blue. And finally, green vertices have no B vertex because yellow color is not in their neighborhood, so they can be recolored by yellow and we obtain that. And that's the only possible thing for complete bipartite graph, and therefore we have this equalities here. Okay, what if we remove a matching from graph? So we delete these edges in a complete bipartite graph. In this case, chromatic numbers is still 2. There is of course no odd cycle, and but the b-chromatic number is n, which is actually equals to m of g, this m degree, for n greater than 2. Let us observe also this. So we start with coloring with all different colors, and first it is possible to this black is not B vertex, and we can recolor it, let's say, by yellow. So now we have 2 yellows here, and actually this will bring us, now yellow will not be in the upper line of vertices. This upper 4 will not be colored yellow anymore. So this means that we will end with a 2 coloring, and this will not be optimal from the respect from maximum number of colors. Why? Actually, these 2 vertices will sooner or later be colored by the same color, which is different than the colors existing in the lower line. And then we somehow end with these 2 colors in the both lines. Okay, these are not all the details, but maybe you can check it at home. So what are the other possibilities? Okay, we can have this. So this blue is not a B vertex, and it can be recolored, say, but by yellow. Okay, if we continue like this orange is not a B vertex, it does not have green, so it can be recolored by green. Then this again gives a 2 coloring. Again, these 2 guys will sooner or later receive the same coloring, and these yellow guys will not have a B vertex because this one will not have a green color, and this one will not have this color of these 2 vertices. So everything will be merged together, and we end with 2 colors. But there is a very natural way, and I think you already know how to how to obtain more colors. So we have this yellow pair already here, but we can continue like that. So we can, this violet has no green neighbor because we have removed this edge, and it can be recolored green. And if we continue, and so this vertex is then recolored red at next step, and this white vertex is recolored black at the end. So we obtained in this case 4 colors, and if n is bigger than 4, we clearly by this procedure we obtain n colors. And of course, now this is 2, this is n, so you see that this b-chromatic number can be arbitrarily larger than chromatic number.
Iztok, last 5 minutes, please.
Yes, thank you. So I will skip these facts about these are some results about this b-chromatic number, and I will skip them as mentioned. So let's go a little bit to the other procedure. So greedy algorithm. produced a coloring as follows. Until we have an uncolored vertex, we give this uncolored vertex a color which is the smallest not present in its neighborhood. This is a very well-known coloring algorithm, and for this we need to check at each stage the colors in the neighborhood of each vertex, and this actually yields this time complexity, which is again polynomial, and the Grundy number, gamma of G, is the maximum number of colors that can be obtained by such a greedy algorithm. Again, a maximum number. So how much these things can go wrong? Trivial bounds, again, the high of G is the obvious lower bound, and delta of G plus 1 is the maximum upper bound, and delta of G means the maximum degree of graph G. Okay, again, let's go to some examples. If we start like that, yellow is the first color, blue is the second color, then upper vertices cannot receive yellow color anymore. So all the lower vertices will receive the first color, so yellow, and the upper vertices cannot receive the yellow, so the first color, so they can receive the blue color. So we end up with this, and we have this line of equalities. So all three parameters are the same for complete bipartite graphs. So Grundy number, b-chromatic number, and chromatic number. Okay, again, if we remove the matching, the same coloring as for the B coloring goes through, and chromatic number is 2, b-chromatic number and Grundy number are equal to n, and this actually equals to the trivial upper bound, the maximum degree plus 1. Okay, so let us see some examples where actually you see gamma is different than b-chromatic number. Here, if we start like that, red is the first color, blue is the second color, green is the third color. So now this vertex has a red and blue neighbor, so it needs to be colored green. This vertex has only blue color, the first color is red, so we can choose red. This neighbor has already first color red in its neighborhood, so it received the second color blue, and so on. We see that now we have this color which has blue, red, and green in its neighborhood, and we need a fourth color. And therefore, this is the lower bound for this gamma of G. But for that this is really equality, one needs to think that we cannot receive at these guys a fourth color. For some reason, okay. Because of lack of time, I will not explain this now. And here is a B coloring. So black has all the colors: green, red, yellow, and blue. So this is a B vertex. This was green. So green is a B vertex, has black, blue, red, and yellow, and so on. So we have a strict inequality here. And now an example where this happens. So we have strict inequality between gamma and b-chromatic number, which is 3 for this graph, and gamma is 7. So the difference is actually 4. If we take this sequence of colors, then it is easy to see that we need to have, okay, sorry, not 7. This is a mistake. This 7 is mistake. 1, 2, 3, 4, 5. This should be 5. Okay. And B coloring is as such. Now, these 3 vertices are, of course, B colors. And why is this B coloring only 3? Because actually M of this G is also 3. It cannot be more. So, by the way, there exist graphs with gamma of G, so Grundy number, arbitrarily bigger than high B of G. You can find more in Matzich and Zacher. Okay, this is actually the last slide, and I just wanted to say that something similar can be done for the other invariants. Whenever you define something by minimizing or maximizing some property, then you can have a similar, you can do similar and check whether what are the difference. This is actually done for domination number, as already mentioned, also for independence number. This was already defined and introduced, but one can do it also for some other parameters or invariants. And that's all from my side. Thank you for your attention.
Okay, thank you very much for the very nice talk. We have very short time for very short question. Is a remark? Yeah, we have claps on the chat. You can ask, you can put your question on the chat or simply directly here in the meeting. Julian, do we have any questions on YouTube or Facebook?
I'm checking it, but I have a question.
Okay, please welcome.
Is this sort of last slide generalizations you talked about, like for packing chromatic? Does there exist something?
Yeah, a very interesting question. I'm not aware of it. And okay, maybe I was too generous here. I mean, you can do it if you have some nice algorithm, some polynomial algorithm for the producing such things. And I'm not sure if this is true for packing chromatic number, for packing packing chromatic colorings. Because if you don't have a fast algorithm, then this has actually no meaning, because I mean, this is essential. We do this, these heuristics are used because they are fast. So, and they give us some results, which are maybe not optimal, but I'm not sure whether for packing chromatic colorings, let's say, are such polynomial time algorithms, let's say.
Okay.
Thank you.
Thank you. I think if somebody wants to ask Iztok about anything, I think we can do it not here in the meeting, but maybe in the chat. So thanks you once again, Iztok, for the very nice talk. And I think it's a time for next point of our conference. Thank you.